Hello, this is Gary Schutz with MathWorks. In this video, I'm going to talk about analyzing and simulating bridge circuits, and I'm going to be focusing today on the directional bridge. Last time we covered the Wheatstone bridge, and today we're going to focus on the directional bridge on the right, and they're nearly identical circuits. The only difference is I have an additional fifth resistor in this bridge, and that is connecting the two voltage dividers. Let's call that R5. And that just so happens to be the resistor where we are going to measure the reflected energy coming back from the load. Likewise, I've got an R1 where I'm going to be measuring the incident wave to the load. So I'm able to essentially separate the incident and reflected power using this directional bridge, and thus the name. So let's think about for a second where this bridge sits in the grand scheme. To do that, let's consider the bridgeless scheme. So on the left, I've got a source voltage and a source impedance or source resistance. And to the right, I have a load. And so again, no bridge. So we would be transmitting from the source to the load. Now, if the load were, let's say, 50 ohms and the source were 50 ohms, the source is 2 volts, then I would have 1 volt drop across R6 and 1 volt drop across RL. And we would essentially have a maximum power transfer in that case, and we would have no reflection. Now, if RL were smaller or larger than 50 ohms, then we would have reflected power, and we would not be able to simply measure a voltage across RL to tell what is the incident power and what is the reflected power, because they would all be together. It would be a combined effect. If we wanted to distinguish what was incident upon the load versus what came back from the load, we would need something like the directional bridge structure or a directional coupler. So in this case, we're using the directional bridge. So instead of having just RL, we're going to have R4. This is the same thing as our RL in the right side, but around it, we've added 4 additional resistors in this bridge configuration. And the particular bridge configuration I have here is called a 10-to-1 sampling bridge, or a 20 dB bridge. And that is because we have 10%, or we're sampling off, I would say 10% of the voltage across R1, and we're maintaining 90% of the voltage across the load that it would be in the bridgeless use case. Now, in order, of course, to create this 10-to-1 sampling bridge or 20 dB bridge, it just doesn't happen by accident. The resistors have to be scaled very carefully. So let's say we were going for a 50 ohm bridge corresponding to our 50 ohm load, nominal load. Then in that case, we're also expecting our source side, in this case, doesn't have to be, but we're assuming it's also a 50 ohm source. Now, in that case, the way you would scale a 10-to-1 sampling bridge would be to make R1 also 50 ohms, R5 50 ohms, and then R2 and R3 scaled by some scaling factor. In this case, it would be, if it was a 10-to-1 sampling bridge, we'd make this 50 divided by 1 less than 10, 9, and R2 to be 50 times 1 less than that 10 number, 50 times 9. So therefore, we'd have 50 ohms for 50 ohms. This would be about 5.555 ohms, and this would be 50 ohms. And of course, R5, the bridge resistor, is 50 ohms. In that case, if you scale it just right, just like that, then you will have at bridge balance, when R4 is 50 ohms at the bridge balance point, you'll have 0 current through R5, because the ratio of R1 to R2 is the same thing as the ratio of R3 to R4. So if you take that ratio, you're going to get 50 over 50 times 9, and that would be 1 over 9. Or if you take 50 over 9 over 50, that's also going to be 1 over 9. So the ratio is preserved. Therefore, you're going to get the same voltage on the left side of R5 as on the right side of R5, again, with respect to ground. And therefore, if you have that same voltage, you're not going to have any current through R5. It's going to be as if R5 were not even there. Now, in that case, because, again, the ratio is 1 over 9, you're going to get 9/10 of a volt drop here and 1/10 of a volt drop here. Again, we're going to have, I guess I didn't say it, but one nice thing about this directional bridge structure, when you use it like this at bridge balance, that the resistance from top to bottom is going to be 50 ohms. It's going to be, the load will appear exactly like the load on the right without the bridge. So if source and load are 50 ohms here, and again, if we use the resistor scaling scheme I just described, it's also going to appear like 50 ohms source and then 50 ohms from the source to ground again. So nothing has changed with regard to how the source views the bridge. Bridge or bridgeless in the case where the bridge balance state. Then the next question would be, well, why do we use something like a k equal 9 or a 10 to 1 sampling bridge or a 20 dB bridge? The reason for that is we would still like to preserve, again, the behavior of the bridgeless case where the power is primarily or mostly directed to the load. So the larger we make K, the more power gets directed to the load. So what we're doing is we're just siphoning off or sampling part of the power that's going to the load to make the incident power measurement. And again, the same thing with the R5 measurement or the reflected voltage measurement. We're only siphoning off a part of what would be directed to the load to make that reflected power measurement. And those ratios are described precisely by the equation see below for V reflect and V incident. For the incident power, it's always the source voltage over 2 times K plus 1. So in our case, K was 9. Therefore, we got V1 over 2 times 9 plus 1, or V1 over 20. And that would be the incident voltage in that case. Or I guess I should have said V2 is 2. I was using 2 volts in my earlier example. So that would be 1 over 2 over 2 times, again, K plus 1. So that's 1/10. You'd have 1/10 of a volt drop across the incident. You'll have 9/10 of a volt drop across the load. Again, at bridge balance, you have no current or no voltage drop across R5. So again, the 10 to 1 sampling bridge is called because we get 1/10 of the voltage dropping across our, I'll call it like our sampling resistor, or where we measure the incident power. It's important to make the distinction that this is not the incident power we're directly measuring the voltage of here at V incident. It's a scaled version of it by this relationship right here. You would have to take the voltage you measure here and multiply it by 10 essentially to get the bridgeless, voltage use case. And likewise with V reflect, it's a scaled version of the voltage that we're actually measuring across R5. That equation is, half of the, again, V1 over 2 in each case, because at bridge balance, you've got V1 over 2 here. So it's V1 over 2 here, scaled by the scaling factor K over K plus 1 squared, and then multiplied by the reflection coefficient, capital gamma, which is the difference between the source impedance and the load impedance or load resistance, and the sum of those two, where again, RS and RL here correspond to R6 for RS and R4 is RL. Now again, all of this only works if you have scaled the bridge accordingly, where R1 equals R5 equals R6, and that would be your, your bridge impedance, what we're calling the 50 ohms in this case. And then R2 would be scaled up by K, R3 would be scaled down by K. And again, that allows us to still approximate the bridgeless use case where we don't alter the behavior of the circuit too much in order to make these measurements. So again, we want to preserve what the load would otherwise normally be doing, but at the same time, we'd still like to sample the voltages to know what the incident and reflected powers are. Okay, next I'm going to share sort of an eye chart of a slide with you to look at what happens to the bridge under different conditions. Under a 50 ohm, the bridge balance condition, when R4 is shorted, when R4 is open circuit with a 2-volt source. And again, we're doing all this with just resistances, real impedances, and with DC voltage source, just to keep it simple. This can, of course, be generalized to AC and reactive loads and reactive components, but we're just keeping it simple for the sake of this initial presentation. So hopefully by taking these three kind of more extreme use cases, 50 ohms bridge balance, short and open circuit, you can get a more intuitive feel for how it works. So let's start at the bridge balance state where we're at 50 ohms at R4, our load resistor. And as I said earlier, if we are at the bridge balance state, then this circuit over here on the left with the directional bridge reduces to the circuit over here on the right, where the bridge reduces to a 50 ohm resistor from top to bottom. At that point, we've got 2 volts across 100 ohms, so we know our current coming in this case, is 20 milliamps. And that's what I've shown here in black. So the black numbers, the black bold numbers, showing the larger fonts, are the case where we are at bridge balance of 50 ohms. So in this particular case, we've got 1 volt. Therefore, we've got if we've got 50 ohms to ground here, we have 1 volt at the top node with respect to ground, and we have the 1/10 of a volt drop across R1. We have 9/10 of a volt drop across R4, and nothing across R5. Likewise, we got a 1/10 of a volt across R3 and 9/10 of a volt drop across R2. Okay, and the way the current splits up in that case is we get, of course, the current is also, you could directly compute that given that we know the resistance and the voltage. We got 2 milliamps going this way, or a 1/10 of the source current, and we got 9/10 of the source current going through R3, the other branch. And therefore, we've got the same thing in the bottom legs. We got 2 milliamps through R2, and we've got 18 milliamps through R4. Again, the black number right here. So that is that's the bridge balance state. Now, what about what happens exactly when we go to the open and short cases? And I should mention, I'm not showing it here, but if you were actually try to formally prove that this load here reduces to 50 ohms when R4 is also 50 ohms and the resistors are scaled accordingly as discussed on the previous slide, then you would have to resort to something like delta to Y transformations of R1, R5, and R3 to come up with, a circuit where you can manage it using parallel and series combinations of resistors to reduce the bridge to 50 ohms. But we're not going through that exercise here in this video. Now let's next take the case where R4 is now shorted out. It's 0 ohms. In that case, always, the voltage across R1 measuring the incident power stays the same. It's still 2 milliamps through it. It's still a 1 volt drop across the 50 ohms. And of course, that's what we would hope for, because if we're measuring incident power to a load, it should not be a function of the load. Only the reflected power is a function of the load. And I should also point out, since I'm using terms like incident and reflections or forward and backwards, that this does have a corollary in S parameters. This would be a single port, or like S1P type of measurement. Since I've only got an input port, I'm not really measuring anything on like an outgoing port. My in and my out is effectively the same port in this case, so an S1P, which allows me to make impedance measurements effectively. Now, when R4 is shorted, when the load is shorted, you can imagine that the overall resistance or impedance of the bridge does drop. And in fact, it drops all the way down to, instead of 50 ohms, it drops to 5.25 ohms. So we've got 5.25. It's like having RL over here at 5.25 ohms in series with a 50 ohm resistor. So the total resistance is just going to be 55.25 ohms as seen by this 2 volt source. So therefore, the current is going to rise substantially from 20 milliamps with that reduced impedance. So now we went from 100 ohms to 55.25 ohms. The current is going to rise up to 36.2 milliamps. And then in that case, we're going to have the same 2 milliamps go through R1. That never changes. We're going to have the other remaining 34.2 milliamps go through R3. And then in terms of how it combines below, we're going to have some current now flow through R5, and we're going to have some current, of course, flow through R2. So there are going to be some different currents. Ultimately, we're going to have 0.2 milliamps go through R2, 36 milliamps go through R4. It'll combine back for the 36.2 milliamps as it is at the source. So the main thing just to note there is, or one of the interesting conditions to note here is that again, the voltage drop across R1 remains the same as measuring incident power. That's going to be, again, either 2 milliamps or 0.1 volt drop. In that particular case, the voltage drop across R5 will be positive from left to right. In fact, it'll be 90 millivolts, and you can actually figure that out shortcut. It's going to be a tenth of the voltage that is dropping across R4 in the balanced state, which is 0.9 volts. So when you're at the extreme short circuit condition, you effectively take the voltage for this particular 10-to-1 sampling bridge, and the reflected the voltage is going to be 10% of the normal or bridge balance voltage at the load. So it just happens to work out like that. Now it's just flip-flop of that when you are in the open circuit condition for the low. So when R4 goes to infinity, you get a flip-flop minus 90 millivolts across the bridge resistor. So there's a switch in polarity going from a short circuit to an open circuit with regards to the reflected voltage that's measured. And you would kind of expect that. I mean, you've got, and that's going to correspond to like an in-phase or anti-phase signal, reflected signal, depending on whether you're open or short-circuited. Now you can also imagine if we do go to an open circuit condition, infinity at R4, the green, that our effective load resistance, actually from the top node to the bottom node for the bridge, is going to jump up to 476.3 ohms. So that means the total resistance as seen by the 2-volt source is going to be 50 plus 476.3 ohms, giving us a reduced current down to 3.8 milliamps. Now, it's also interesting, some of these relationships that pop up in this sort of bridge when you scale it accordingly, because now if you take the sum of the open circuit current and the short circuit current, or I should say it like this, the short circuit current in red and the open circuit current in red, if you sum them, you get 40 milliamps, which just happens to be twice the current that we started with in the bridge balance. Likewise, the voltage from the top node to ground across the bridge from top to bottom, it goes up to 1.81 volts, given that we got a smaller drop across R6. And the sum of those two voltages at the short and open circuit conditions adds up to the source voltage. And so you get these interesting kind of relationships that occur with the bridge, again, is scaled accordingly. And then the purple numbers that I've shown here, I haven't talked about those yet. That's just the percentage of the power that's going to be dissipated at bridge balance, again, using this scaling scheme. So if you got 0.9 volts versus 1 volt, you're getting 81% of the power, 0.99 times, 0.9 times 0.9 is 0.81. So that would be 81% of the power is directed to R4 using a 10-to-1 sampling bridge. And of course, finally, this is where the other power is dissipated. It goes 1% here, 9% here, and 9% here, all adding up to 100%, again, as compared to the bridgeless condition. All right, so that was a lot to say about this very, very simple circuit. In the next slide, which we're not going to say much about, I'll kind of go into the demo soon. I just showed it, we can use this with this is supposed to denote here a 5-volt AC sort of signal. I didn't indicate that very well schematically, but it's a 5-volt AC signal, 5-volt peak. And going between, in this case, instead of going between open and short, I just said, let's make the load a little smaller than 50 ohms and a little larger than 50 ohms, so plus or minus 5. And then what happens to these reflected and incident voltages? Well, again, the incident power is always the same no matter what the load is. It's 0.25 volts. And again, in this case, yeah, if it's 0.25 volts, it's essentially 1/10 of what it would be otherwise. It would be 2.5 volts in the non-bridge case if you had a 5-volt source, and here it's 1/10 of that at 0.25 volts for a 10-to-1 sampling bridge. Notice if it goes down to 45 ohms that we get a reflected voltage, again measuring from left to right, that is in phase with the source, with the incident wave. If we have a load that is slightly larger than the nominal, our bridge impedance, the 50 ohm bridge, 55 ohms, let's say, then we get an inverted or anti-phase reflected voltage. Okay, so it's not just at the extreme conditions where you get some these anti-phase. In this case, for the DC, you also get, you can see these inversions happen as you move around 50 ohms. Again, with the same equations apply. The incident wave it follows this, the reflected wave follows this, where the reflection coefficient is the last term. You can also, of course, use this circuit to measure the reflection coefficient. So you can imagine if you solve for RS minus RL over RS plus RL and leave that, and let's say on the right-hand side, and you put the K over K plus 1 squared and the V 1 over 2 on the left-hand side, then you would have effectively, by measuring the reflection voltage and knowing V1 and knowing K, you've solved effectively for the reflection coefficient of this, for the given scheme or the given load you're using. Okay, so now we are over in Simulink. I've modeled the directional bridge using Simscape components, and then I've monitored the various nodes. I'm calling this the top node, the ground node, the left node, the right node. And then those are kind of shortcut connection labels, so I don't have to drag wires over to measure those voltages. I'm displaying them on scopes, and then I'm using them also to compute certain parameters like coupling, directivity, isolation, and insertion loss. And effectively, it's the same bridge I was showing in slides earlier, where I've got a 50 ohm bridge, and I'm scaling the resistors using the 10-to-1 sampling bridge concept. So this would be 50 divided by 9, and this would be 9 times 50, and 50. And right now I'm at the bridge balance state where the load is also 50 ohms. So let me run this very quickly, and then we'll just see kind of what numbers come out of it and look at some waveforms. Okay, so let's pull up our waveforms on the right and just see if these make any sense. The first I'm going to point to is the flat line at the bottom. Since I'm at a bridge balance state, I have no current or voltage drop through R5 or no voltage drop there. So we see a flat line for V reflect. Okay, that would be L to R on this V reflect scope. Now, if we look at V, let's call it VN. VN is what I'm calling from top to ground, okay, across the bridge in the vertical direction. That is 1 volt, okay, because in this case I have a 2 volt peak to peak sine wave over here at the source. So half drops here, and then half drops again across the bridge. So that makes sense. And then 1/10 of a volt peak to peak, again, or I should say peak, drops across where I'm measuring the incident power across R1. I'm calling that V coupled. And then as far as what's dropped, again, nothing drops across R5. And if we were to look finally, if we want to look at what drops across VTX, it should be the remainder of the voltage to add up to 1 volt. And so let's just look at it, wherever it's hiding on my screen. And again, it's up to about 9/10 of a volt, which is hard to see there. You can see it a little more accurately there. So got 1/10 of a volt on R1, and I have a 9/10 of a volt at the load. If it were no bridge, we would have 1/10 of a volt. I mean, a full 1 volt peak across the load. So we've taken away a little bit of power from the load to make this power measurement, incident power measurement. And in fact, that's what the insertion loss is in this case. We've lost about a dB of the signal in order to make this, these power measurements. Next, let's make the load a little smaller. We'll make it 45 ohms as we did in the slides earlier, and I'll run it again. And what we're going to find, if we look at our V coupled and our V reflected, we'll see the coupled is the same. It's still 1/10 of a volt peak. but the V reflected is in phase. It's smaller. It's about 4.76 millivolts peak, but it is in phase with Vn and V coupled. Now, if we were to change it, if we were to go to 55 ohms instead, not 50, not 45, but 55, run it again, and then we look at the various signals, we will see that V reflect now is out of phase with Vn. Okay, it's in fact exactly inverted. It's about a 4.3 millivolt peak signal. So using the scheme, you can see it's very easy to tell just by the polarity of the reflected voltage whether we are closer to a short or closer to an open as we go under 50 ohms or above 50 ohms. Okay, so that's all I'm going to say about the introduction to the directional bridge. However, in the next video, I will get into using the directional bridge applied to reactive loads, and then how you would use that directional bridge and your device under test to measure S parameters. So please stay tuned for that. Thank you.